All Earth's desert sand fits into a sphere 79 kilometers wide. That's 8 times bigger than what killed the dinosaurs. We know sand is weathered rock, silicon dioxide. The question isn't what it's made of, it's how this much ended up on the surface. 22 million square kilometers of sand-covered surface, bigger than Russia. So where did it all come from? Let's investigate. Standard geology explains desert formation through millions of years of erosion, wind, water, and temperature cycles grinding rock into fine particles. That's well-established science, but there's a gap in the math that's worth exploring. Let's start with what we know. Sand comes from weathered rock. It takes millions of years of wind, water, and geological pressure to produce it. That's the textbook explanation, and it works for individual grains. But here's a question. If it forms slowly, why is it all sitting on top? If sand forms over millions of years, why isn't it buried under 10,000 years of soil and vegetation? Why does the Sahara sit on top of the land instead of underneath layers of dirt? The standard answer is wind. Wind exposes it, moves it, concentrates it. That's plausible for redistribution, but it doesn't fully explain where the volume came from in the first place. So let's run a calculation, a straightforward one that surprisingly doesn't appear much in the published literature. How big would a single rock need to be to produce all of it? Step 1. I pulled the area of every major desert from Wikipedia and cross-referenced it with the World Wildlife Fund database. There's actually a discrepancy between sources. The WWF lists more desert area than Wikipedia. We use the conservative number 21.9 million square kilometers of desert excluding Antarctica. Step 2. Average depth. Desert sand dunes in the Sahara reach up to 300 meters tall, but averaging across the full desert, including thin layers, rocky plains, and high dune fields, a conservative estimate is about 12 meters. Step 3. Volume equals area times depth. 21.9 million square kilometers times 12 meters gives us roughly 260 trillion cubic meters of sand. That's enough sand to bury every city on Earth 10 meters deep. Step 4. If, as a thought experiment, that sand came from a single spherical body, what size would it be? We use the formula for the volume of a sphere. Solving for radius, then doubling for diameter, the answer is 79 kilometers. 79 kilometers. Let that number settle for a moment. For perspective, the asteroid that killed the dinosaurs, the Chicxulub impactor, was about 10 kilometers across. This hypothetical sphere would be 8 times larger in diameter. So could something like that actually exist, and could Earth survive it? Now, let me be clear about what this is and isn't. This is a thought experiment. I'm not claiming this happened. I'm asking, what if we follow the math and see where it leads? The question is whether it's even physically possible. Let's test it. Could it have been a comet? Comets are mostly ice and gas. The largest known comet nucleus, Halley's, is about 15 kilometers long. Comets are roughly 80% gas and water. They don't deposit sand. Some researchers have pointed to Comet Biela specifically, but Biela was a short-period comet that astronomers watched disintegrate, far too small and too icy to produce sand on this scale. What about iron asteroids? Same problem. Iron doesn't become sand. What does produce sand? A silicate asteroid, essentially a rocky body. According to planetary science, upon impact it would vaporize and disperse as fine particulate matter rich in silicon dioxide. That's what sand is. But there's a problem here. A 79-kilometer silicate body hitting Earth in a single impact wouldn't just deposit sand, it would blow the atmosphere off. It would sterilize the surface. Life wouldn't survive. So we're stuck, unless we drop one assumption. What if it didn't land all at once? Here's an alternative scenario to consider. What if a large rocky body broke apart before impact, fragmented by tidal forces? The debris field could have hit Earth over years, maybe decades. Not one catastrophic impact, but thousands of smaller strikes. In this model, heavier fragments would fall first, leaving craters. Then a ring of fine debris, like an accretion disk, could settle around Earth's orbit and descend gradually. Clay particles, being heavier, would descend first, mixing with atmospheric moisture and falling as muddy rain. The finer, lighter quartz sand would stay aloft longer, descending over additional decades. If that sounds far-fetched, consider this. We already know Saturn's rings work on a similar principle. This phase descent model would explain something interesting. Why the sand layer is relatively even across continents, and why we don't see one massive impact crater. Since the debris disk would align along Earth's ecliptic plane, between the tropics, the heaviest deposits would concentrate in equatorial regions, which is interestingly where we find the largest deserts. That's an interesting pattern. But patterns aren't proof. We need something harder, historical records. If sand was falling from the sky recently, somebody would have written it down, right? People in the 19th century had printing presses, newspapers, scientific journals. If unusual atmospheric events happened, there should be a paper trail, and there is. A Russian researcher spent months going through a 19th century weekly called Vesemerная Illustratia, World Illustration. It ran from 1869 to the 1890s and covered global news. 59 volumes, over 25,000 pages. Now, it's worth noting, this is a popular magazine, not a peer-reviewed journal. These are period accounts, and they may contain exaggeration or misinterpretation, but the volume of reports across different regions is notable. In 1869, Volume 1, page 287, the journal reports repeated sand rains over Naples, Calabria, and Sicily. Not dust storms, sand rains, falling from the sky at wind speeds over 60 kilometers per hour. The official explanation: Saharan wind carried it across the Mediterranean. That does happen, but what came next is harder to explain. On the very same pages, the journal shows an engraving of the streets of Tashkent, thousands of kilometers east of Naples, deep in Central Asia. The streets are buried under meters of soil and sand. You can barely see the buildings. Naples and Tashkent, same publication, same time frame, over 5,000 kilometers apart. Saharan wind does not reach Tashkent. Whatever was depositing material was doing it on a continental scale. And it gets stranger. The climate was acting up too. That same winter of 1869, rivers in Warsaw broke free of ice in January. Flowers bloomed in Kiev in late January. Cherry trees blossomed in February. An abnormally warm winter across Europe and Central Asia. That's the kind of atmospheric disruption you might expect if the upper atmosphere were loaded with foreign particulate matter absorbing and re-radiating heat, though there could be other explanations. In 1870, more anomalies. Astrakhan floods. In 1871, a fog so thick in Uratayub, Tajikistan, that you couldn't see 3 steps ahead. When it settled, it left a residue. Not water, dust. Then there's the hail. In Azerbaijan that year, hailstones fell, and when they melted, there were pieces of stone inside. Stone fragments wrapped in ice falling from the sky. That's consistent with rocky debris entering the upper atmosphere and getting coated in ice while passing through moisture-laden cloud layers. In 1872, Italy reported sand rains again, this time attributed to a Vesuvius eruption. But the sand fell across the entire island of Sicily, 300 to 450 kilometers from Vesuvius. A bluish, dry fog appeared in Turin, 350 kilometers north. The entire Italian peninsula was covered by clouds dropping sand, accompanied by lightning and falling temperatures. A 1,000-kilometer footprint. That's not a volcano, that's something atmospheric. That same year, near the coast of Florida, divers at St. Augustine reportedly found submerged ruins 14 kilometers offshore, and in August 1872, New York City witnessed 241 meteors in a single night over 4 hours. Scientists attributed it to the Perseid meteor shower, but standard Perseids are particles the size of dust grains. They don't produce noise and rumbling. These reports describe something larger entering the atmosphere. Then came the red rain, and this one has chemistry we can check. Near a French town that same year, a blood-red rain fell. Chemical analysis at the time found iron compounds, aluminum, silicon, and carbonic acid. Those are the building blocks of a carbonaceous chondrite, the most common type of asteroid. Iron, aluminum, silicon, carbonic acid, those match the composition profile of carbonaceous chondrites. It's an intriguing correlation, though red rain events have also been attributed to algae and Saharan dust. In November 1872, over Alexandria, Egypt, another massive meteor storm, approximately 200 meteors per minute for over 6 hours, many as bright as Jupiter. 200 meteors per minute for 6 hours, that's not normal. In 1873, in southern Russia, a dark cloud appeared during perfectly calm weather. It flickered with silent lightning, and between the cloud layers, witnesses reported seeing a comet-like object with a long black tail. A dark tail is unusual. Normal comets have bright tails of vaporized gas. A dark tail would suggest a body shedding rock debris, which is what a fragmenting silicate asteroid might look like. Now here's where the story takes another turn. Multiple nations suddenly wanted to flood the Sahara. In the late 1870s, England, France, Belgium, Germany, Spain, Portugal, and the United States all sent expeditions to the Sahara. Their goal: dig a canal from the Mediterranean and turn the desert into a sea. Engineers confirmed it was feasible. The canal would only need to be about 30 kilometers long. But here's the puzzle. Why would anyone try to flood a desert that had supposedly been there for millions of years? What if in the 1870s the Sahara was much flatter and lower than it is today? Trade caravans regularly crossed it. Merchants confirmed the route was passable. Today, that crossing is impossible on foot. Something buried those trade routes under hundreds of meters of sand. And based on these accounts, it may have happened between the 1870s and the early 20th century, within documented history. Not millions of years ago, possibly within living memory. A French explorer named Paul Soleillet crossed the Sahara in the 1870s. He described the landscape far less desolate than we see today, with numerous ruins in the most sun-scorched areas, evidence of a fairly advanced civilization. Ruins now buried under sand so deep that no modern expedition has relocated them. At the Suez Canal opening in 1869, engravings show Egyptian temples buried in sand to their rooftops. If an orbital debris ring were gradually descending into Earth's atmosphere, you would expect exactly this sequence: first heavy fragments, then clay, then sand. Each phase producing different atmospheric phenomena, from meteor storms to red rain to sandfalls. But if this really happened, why isn't it in the textbooks? That's a fair question. These reports come from a popular magazine, not peer-reviewed science. Period journalism mixed observation with speculation. Some volumes of the source journal have been lost, which could mean anything from poor archival practices to deliberate removal. And the Sahara flooding project itself, multiple nations confirmed it was feasible, expeditions proved it could be done, and then it was quietly abandoned. The sand may have simply kept accumulating. Now let's revisit the math one more time. If we include not just deserts, but all sand and clay on Earth's entire surface, land and ocean floor, the hypothetical sphere grows to roughly 198 kilometers in diameter. 198 kilometers, 20 times the dinosaur killer. That's the distance from Moscow to Ryazan. Larger than Sardinia, an object this size hitting Earth all at once would destroy the planet, which is precisely why, if it happened at all, it had to be a distributed event. A gradual debris field spanning years or decades. That's the only scenario where life survives. But infrastructure and civilization take a serious hit. So here's where we land. The calculation is straightforward. Anyone can verify it. All Earth's desert sand compiled into a sphere gives you a body roughly 79 kilometers across, 8 times larger than the Chicxulub impactor. That doesn't mean that's what happened, but it raises a question worth asking. What produced this enormous volume of fine silicate material, and why is it all sitting on the surface? 19th century accounts describe unusual atmospheric events that are at least consistent with the hypothesis. Three possibilities remain. 1. It accumulated gradually over millions of years through erosion. The textbook answer, though the surface layer question lingers. 2. A distributed debris event. 3. An explanation we haven't considered yet. What I find interesting is that this specific volume calculation, total desert sand converted to equivalent body size, doesn't seem to appear in the geology literature. The math takes 10 minutes. Any geology student could do it. Sometimes the most interesting thing about a field of study is the question that hasn't been asked yet. In the next video, we'll look at what a distributed impact event would actually do to a civilization, and whether the historical record contains what you'd expect to see if one happened a few hundred years ago. If this made you think, subscribe. Every video here is an investigation.